brings us to the study of homology. Where should I write? Well, oh, by the way, it's easy to see over here in this example that if you were to take the boundary operator again on these, right, they work out to 0. Because you get like, you know, what is the boundary operator on 2, 3, by the way?
3, -2?
Yeah, it's P3 minus P2, right? And so this gives you like P3 minus P2, P1 minus P3, P2 minus P1, and they just cancel. So you can see that partial squared is 0. In other words, the boundary of the boundary is nothing, right? So the boundary of the boundary is empty.
I'm not sure there's a lot of different areas of mathematics that have boundaries are...
The boundary of the boundary should be empty? Yeah, I think that's probably one of the things you want to see for a boundary, whatever you're defining to be a boundary. Yeah. All right, so I have titled this lecture Elementary Homology Theory, so I probably better tell you what do we mean by homology. And so here's the definition. An M chain C bar with boundary of C bar equals to 0 is an M cycle. All such M cycles form ZMK. All right. Likewise, an M chain that is the boundary of an M minus 1 chain M plus 1 chain rather, is called an M boundary. It's called an M boundary. So let me just give you, like, that means that you've got like C bar is equal to the boundary of C bar prime for C bar prime in C M plus 1. Okay, and then we say the set of all of those is BMK. These are the boundary cycles. Or the boundary M chains. Definition, 2 M cycles are homologous. Homologous, and we write Z1 bar squiggle Z bar 2 when Z bar 2 minus Z bar 1 is an element of BMK. This is another way of saying that Z bar 2 minus Z bar 1 is equal to the boundary of some like C prime for C prime in CM plus 1K. All right. Then bracket Z bar is the equivalence class. In other words, it's let's say W bar in ZMK such that W bar is homologous to Z bar, right? And in this context, if we take ZMK, come on, ZMK mod this equivalence, right? In other words, this is, as a quotient vector space, this is ZMK quotient BMK. See, because what we're saying is that two cycles are equivalent if their difference is simply an element of the boundary space. That's a quotient vector space, and this by definition is the mth homology group of K. With real coefficients. Furthermore, the dimension of HM rather, of K is beta sub m, which is, by the way, the mth Betti number. So, you might say, well, this is lovely and all, but what does this have to do with about like the shape of a space, right? Because everything we're doing so far, it just has to do with a polyhedra, right? A polytope, something like that, yeah? So, or maybe we can take unions of polytopes and still calculate things like that, maybe, right? I'm not saying it's just a polytope. I mean, a simplicial complex may allow for a little bit more than just that, right? But what about other spaces? Well, this is where the concept of triangulation comes into play. A triangulation is basically a homeomorphism of a simplicial complex, an oriented, well, for us, we're going to talk about an oriented triangulation. It's a homeomorphism that is a one-to-one continuous map with continuous inverse from your simplicial complex to your space. And when you study the theory of topology more properly, what you'll find out is that the homology of your space is in one-to-one correspondence with the homology of the simplicial complex. In other words, calculating the homology, the homology groups of the simplicial complex gives us a tool to calculate the homology groups of space. There's other ways of defining homology on an abstract space which don't involve direct, concrete, geometric constructions like we've been doing today. All right, there's other things like the de Rham cohomology we talked about before. It turns out is in one-to-one correspondence with these things. That was a very different thing, wasn't it? The de Rham cohomology involved the different, like comparing exact forms versus closed forms, right? If we had a closed form which was not exact, that led to a non-trivial cohomology group. You know, we found one. We know that the angle function, right, the differential of the angle function is closed in the plane, but it's not exact because we can't define, you know, the angle function continuously all the way around. But like, is that it? If we look at the punctured plane, is that the only non-trivial closed but not exact form in the plane? Is it just the angle function? Is there more? See, if you just look at that from the perspective of de Rham cohomology and the study of differential forms, that's a very intimidating, for my taste, a very intimidating question. On the flip side, if you ask me, can you calculate the homology of the punctured plane? Well, that I can do because that's the same as the homology of the circle. And the homology of the circle, well, how do you triangulate a circle? So we have triangle, not the shaded one in, the shaded triangle, and the tetrahedron. These are each a simplicial complex, K, K, K. I regret nothing. And then over here, over here, M, 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 and this can be clipped out of context and used against me by my enemies. You know, I support Trump, so you know that makes me a Nazi. So I've heard. Let's see here. I need to look at my channel comments. I have some like, why do you support Trump? Like, well, it's not so much that I support Trump. It's just that the alternative, good grief, you know. But so, I mean, would I have supported Trump 10 years ago? No. Like, probably not. But I don't know if you've noticed or not, but the world's gone mad. Let's see here. So what I'm trying to get at is just the edge of the triangle, the solid triangle, the tetrahedron, all right? And this, I mean for that to be the solid ball. Disc. Circle. All right? There is a homeomorphism from each one of these simplicial complexes to those spaces. All right? Don't make me write down the formula for it. I'm going to prove it the same way my topology professor did in grad school. Wait a minute, undergrad? I might have been undergrad at the time, but it was a graduate class. So, blow up. So basically just imagine sticking the triangle in here, right? And then you can just bloop, 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 bloop. And that's a continuous process, and it's obviously invertible, right? Clearly. Yeah, I mean, all of the topology questions I put on your final you can solve like this, unless they're the ones about the Lie group. I mean, the matrix. I did give an interesting topology question about matrix groups earlier, right? Show that the general linear group is open and the orthogonal group is closed, that stuff. But yeah, these are all actually all homeomorphisms. And when we study algebraic topology more carefully, or if you just read Rentlen, he explains that if you have a homeomorphism, it transfers the simplicial homology here to the singular homology over here, which is defined in terms of sort of blown up triangles. And they're the same. And de Rham proved a theorem that his cohomology, that's defined in terms of differential forms, is also discovering the same data about the space. Like, basically this is a way of detecting whether or not there are holes or higher dimensional holes in your space. And that, in a nutshell, is topology. Topology, more generally, is the study of like abstract analysis, all right? So, now I can calculate the actual homology for a circle and, for a sphere and a few other things. I'll probably do that next class for you guys if we need to. I need to look at your homework and scam likely. I need to mute scam likely. So I don't, it's my son. I don't remember, guys, offhand, but if I need to actually show you a calculation of the homology group or not, like it's just straight linear algebra, but it is not natural. I would say it's not natural. The example I showed you today, setting up C0 and C1 and C2, like that's a good part of the calculation. So we just kind of build off of there, explicitly look at what the boundary operator does, and that will write down a matrix for it. And once we can calculate the matrix, we can calculate like rank nullity theorem stuff. If we need to look at that next time, we will. But if we don't, we won't. That's not really what this course is about so much. What this course is more about, of course, is differential forms. And so I want to show you what we're doing. Up next is we're talking about how do you integrate, given alpha is equal to like the sum, over, alpha I dxi, right? And so here a P form, you know. Then if we have the integral over m of alpha, what do we mean by that? You know? Then what we mean by that, and this in order for this to be meaningful, it will have to be this. This is going to be the pullback of alpha to the set that, you know, so here I'm thinking of phi as a chart that goes from M to, let's say, a subset of RP. So M has to be a p-dimensional space for this to make sense. And so here's what happens after the dust settles. It's just like rats. Here's a simpler example. If I had g dx wedge dy wedge dz and I was integrating over like a volume B, you know, how do you define the integral of this 3 form over the volume B? The answer is you just drop the wedges. And it's just the ordinary triple integral. But I'll explain this next time, that if we integrate, we can integrate a k form over a k-dimensional space, and this notion of form integration will recover our previous notions of like line integral, surface integral, volume integral, all those things. And the really cool thing is we learned that there's something called the generalized Stokes theorem, which says that if we integrate the differential of a form alpha over a manifold, it's actually equal to the integral of alpha over the boundary of the manifold. And the proof of this so-called generalized Stokes theorem will be greatly aided by our discussion today, because essentially the issue here is like, what do we mean by boundary of a manifold? Well, I think maybe you can start to see how we would define that. If we had a triangularization of the manifold, the boundary would just be what happens when we, you know, let the boundary operator act in the triangulation. It would naturally induce the edge of the space for us with the appropriate orientation already. As opposed to how we did that in Calc 3, which was through a system of ad hoc rules that we all agreed on to half learn and not take off too much partial credit for when they were not adhered to, yes. But anyway, that's it for today. Unless you guys got a question, but it's still it for today. Yeah.
So earlier I asked a question and I'm not sure if I understood your answer.
Uh-oh.
I'm not sure if we were understanding each other. So like when we were talking about the tetrahedron.
Uh-huh.
And then, so that's like a, what was that defined as?
What is a tetrahedron? It's 4 points, so it's a 3 simplex.
3 simplex.
Yeah.
So I guess, so what I was asking is if you can make up a 3 simplex of like 4 2 simplexes.
Can you make up a 3 simplex?
Yeah, thinking about this.
In that case, it's a simplicial complex.
Right.
Yeah, I mean, you can do stuff, I think, like a bow tie. Right? That's like, I think this would still be a simplicial complex because the only place they meet is on a vertex, which is a common face. And that's, you know, as long as I include all of the subfaces of each triangle, I think the union of these two triangles would form a simplicial complex. Yeah?
If you take 2 bow ties, then you could form a tetrahedron. So tetrahedron is like...
Well, I don't know. I mean, I have to think about that. Like way things get intertwangled is, I gotta be careful. You know, like the defining condition, the meeting along a common face. I had to think about it, but...
If you could take a tetrahedron that has a simplicial complex.
This I think might be a triangulation for like a figure 8 space, maybe. I don't know.
That makes sense.
So that probably has a pretty interesting homology. By the way, I said homology over the reals. There's homology over other groups, but that is a story for another day. I should stop here.
Thank you, Dr. Jordan.
Uh-huh.